So, hello, I'm Somesh, and we'll start with quantification of the charge domain size and stored charge. So, your small charge domains are injected in the PMMA film using this charge electrification method by placing the tip and the sample in close contact, and the 5 voltage is applied during 25 ms. So, in the charge domain size, uh, it is controlled by changing slightly the loading force. So with this procedure, positive charge domains with a lateral size and the order of the tip radius are obtained. So top panels of figure 8 shows the VFM SKPM image of three charge domains of different size obtained at a fixed scanning tip sample distance z equals to 8 nanometer. Recalling the equation 8, the VSKPM image can be expressed as this. The figure 8 is this, and you can watch 8A, B, C, and so this was the formula VFM SKPM XYZ equals to Z naught minus 1 by 2 U1 double dash apex XYZ equals to Z naught plus U1 double dash cone XYZ equals to Z naught upon U2 double dash apex Z equals to Z naught plus U2 double dash cone XYZ equals to Z naught plus V naught CP. And the V naught CP is the contact potential in the absence of charges, when the charges are not present. So as seen in figure 7 before, in the present images, the working distance is small enough so that the equation 13 u2 double dash cone is very less than u2 double dash apex. And yeah, so here u2 double dash is nearly equal to u2 double dash apex. So, with this assumption, the size and the total storage charge are obtained by fitting experimental VSKPM FM lateral profiles to the theoretical model proposed in section 2.3, which is finite size charge domain. Uh, as the measurements are performed at a known tip sample distance, the only fitting parameters used are domain size R and the total charge Q. So in the figure 8, the fits are excellent in all three cases, indicating the validity. Simple model used. The charge densities are as given, sigma A, B, C, and these charge densities are in good agreement with the ones obtained in 10. So as we mentioned before, we have neglected U2 double dash cone in the previous equation. If this if this contribution were non-negligible, the fits would still look similar, but the value of Q would be wrongly estimated. Our simple model also neglects U1 double dash cone XYZ equals to Z naught in the numerator of equation 13. So in this case, quality of the fits indicate that this contribution must be small, at least at this tip sample distance. It means under this working condition, the proposed model accurately estimates the total charge and domain size. It also confirms that for this charge injection protocol, the constant density domain charge model is adequate. So if we take into account the charge spread into the volume, the charge estimation would be slightly larger than the same charge located just at the surface. However, our working conditions, this effect is small. You can look at the diagrams here, 22 nanometer, 50, 80. To further validate the previous results, VSKPM FM x equals to 0, y equals to 0, the spectroscopy curves have been measured on top of the charge domains of figure 8. So the you can see the VSKPM here, and the lateral distance nanometer is here, and the sphere charge domain model reproduces the experimental VSKPM FM data at small tip sample distance. But it fails at distances larger than about 1 or 2 tip radii. So it is because the spherical tip model neglects the cone contribution at large distances where it cannot be ruled out. So you should note at a fixed distance the numerator of equation 13 it is just a constant. independent on the localized charge. So, using the proposed model to fit charge profiles from VSKPM FM images, charge domain size and the fit quality would not be affected. In order to determine the determine the relevance of the cone contribution at large tip sample distances to the U1 double dash contribution, we analyze the experimental U1 double dash is equal to 0 data. So, interestingly, as shown in the figure 9b, the figures are 9a, b here. When the experimental U1 double dash are plotted together with the corresponding theoretical ones, so they perfectly agree for the tip sample distances without the additional free fitting parameters. So, indicating the charge rated term U1 double dash is less sensitive to the cone contribution than the capacitance rated term. So, in UHV, short tip sample working distances can be easily achieved, and the cone contribution to the VSK PMFM can be neglected. On the contrary, in air conditions, due to the hydrophilic character of the sample surface or due to technical limitations, typical tip sample working distances are much larger, and the contribution of the microscopic part of the tip may not be ruled out. So, overcome this problem, in order to simplify the data modeling and to obtain quantitative information of the localized charges, instead of the VSKPM FM, the U1 double dash ZQ epsilon R, the signal is more adequate, and experimentally VSKPM FM and the U2 double dash images are recorded simultaneously by using a two-channel lock-in. So then the U1 double dash xyz equals to z naught epsilon r in the image is reconstructed. U1 double dash minus equals to minus 2 v skpm fm into U2 double dash. So finally, it should be noted that the VSKPM image analysis only works if FM KPM mode is used. If a similar analysis is performed on VAM SKPM images of small charge domains, it is not possible to accurately fit neither the lateral profiles nor the spectroscopic curves. And uh, so it, it is not possible to like fit the spectroscopic curve. This indicates that the contribution of the microscopic parts of the tip are relevant not only in the capacitance related term but also in the U1 dash term. And you can see the diagram, this figure 9, tip sample distance in nanometer, VFM kpm here, and d to U1 dz square. So, the conclusion, moving on to this conclusion, in this work, we have proposed a methodology to analyze SKPM images when small localized charges are present on thick dielectric surface in order to obtain quantitative information about the total stored charge and the charge lateral size. A rigorous protocol to characterize the tip geometrical parameters and the epsilon r of the dielectric material is presented. So, since the Kelvin voltage drastically depends on them independently of the SKPM mode used, AM SKPM or FM SKPM, operating the SKPM at short enough tip sample distance in the FM SKPM mode, the V FM SKPM images can be accurately analyzed, neglecting the tip cone contribution with a simple spherical tip image charges based model. So otherwise, the contribution of the microscopic cone should be taken into account, which appreciably it increases the numerical effort, and data analysis renders more difficult. So it has been found that the cone effect mainly contributes the VFM SKPM through the capacitance related due to double dash Z epsilon r theta, uh, while the charge dependent U1 double dash term is less sensitive to it. So, to avoid the cone effect in ambient conditions, the operating tip sample distances are typically large. We propose to use the U1 double dash signal to obtain more quantitative results. So, finally, we highlight the theoretical model proposed can be easily implemented to model complex surface charge distributions. In order to determine the charge distribution of a general system from Kelvin voltage image, the inverse problem should be solved. So it's a challenging task, with the simplicity of the image charges method together with the evidence that the U1 double dash Z Q epsilon R term can be correctly modeled with a spherical tip approximation, even at relative large tip sample distances, such that this is not out of reach, and and will be addressed in a future work. So, so that was it for now.